in the theme of logistics, storage, and infrastructure. The three things that energy transition cannot do without. The world sits today at a very pivotal moment on energy transition, even more so for India. And while we'll all talk about generating green power, energy security, more refineries, more solar power, more wind, and so on. But really, we do not talk what happens behind the curtains, right? And that's where the three things, right? It's all about not just generation, but it's also about storing it, moving it, and installing it. And that's the reason we're going to talk a little bit more about what goes behind the scene. It's our privilege to have three and maybe a fourth speaker as well, who will talk very innovative, interesting ideas about energy, storage, infrastructure, and logistics. Without further ado, let me welcome our first speaker, Mr. Subramaniam. Mr. Subramaniam is a principal geotechnical engineer with Mcdermott. And today he's going to talk and unravel what goes behind pipeline installation, especially for gas and oil pipes in exploration. And when I was talking to him, he just told me that there is a lot of science that goes behind soil interaction with pipeline. So over to you, Mr. Subramaniam, for the next 15 minutes or so. Thank you.
Thank you, Mr. Shah, for the nice introduction. Good afternoon, one and all. So in this presentation, I am going to detail about our recent experiences in the offshore pipeline installation and the embedment of the pipeline into the soil. So there are wide range of embedment prediction models are available. So in this study, we examine the robustness of the existing embedment models and how we can improve the models for the better prediction of the pipeline embedment. So this is the overview of the presentation. So some introduction and importance of the study, and what are the different available vertical load embedment models and methodology adopted in this study, and the pipeline properties considered in the study and the seabed characteristics in which the pipelines are installed, and the 5-point survey data or ASLIDE embedment data, and some statistical analysis of this ASLIDE embedment data, and some method to improve the existing models, how we can improve the existing model predictions. So the subsea pipelines are either installed in the seabed surface or trenched and buried. So the surface burial or trenched depends on the water depth and the thermal requirements and the cost and the safety of these pipelines. So even though we install the pipelines on the surface of the seabed, the pipeline gets embedment into the soil, depends on the pipeline characteristics, soil characteristics, and installation methods, as well as the whether we go for relaying or J-lay or S-lay methods. So once the pipeline gets embedded into the seabed, either 30%, 40%, or 50%, it affects the different pipeline design parameters. For an example, on bottom stability, if the pipeline gets embedded into the soil more, then the lateral friction factor increases, but it ensures the overall stability of the pipeline. Similarly, it retains the heat and retains the thermal properties or keep the pipeline bit warmer. Similarly, when the pipeline gets more embedded into the seabed, the free span gets reduced and there is less span length. Similarly, it reduces the vortex-induced vibration or the amplitude of vibration and increases the fatigue life of the pipeline. But in terms of global buckling, when the pipeline gets more embedded into the seabed, the critical buckling forces increases. It may prone to buckle because it cannot free to move. In case of surface laid pipelines, the force can get exhausted due to the displacement. Similarly, in the axial walking, the axial friction factor increases. That's how it improves the axial movement of the pipeline. So how we can predict the embedment of the pipeline into the seabed, how much it can embed. So there are different models are available. The work started in the early 1980s. Murphy et al. Come up with the embedment prediction models based on the pipeline weight, overall diameter, and undrained shear strength. So if we see these different embedment models, the critical parameters are pipeline weight, pipeline diameter, and most importantly, the undrained shear strength or remolded properties of the soil. So these influences the pipeline embedment. And different models has been come up considering the pipeline heave as well as the bearing capacity of the soil. So notably, in the recent development in 2021, DNV has come up with the two pipeline embedment models that is known as pipeline model 1, model 2. Now we will go more talk about these two models because these are the two models widely adopted in the clayey soils. So model 1 mainly based on the bearing capacity theory. Model 2 depends on the empirical formulations. So what DNV has done based on the SafeBuck industrial project, they have collected wide range of pipeline embedment data and they have come up with this model. This is widely adopted for the soft clay soils. So the methodology adopted in this study, so we collect the soil properties and derive the design soil parameters and we design the pipeline, we install the pipeline. Once the pipeline got installed, then we measured the as-slide embedment. So how much is the actual embedment using the 5-point survey data, which I will explain in the coming slides. Once the data is collected, then we have compared with the actual embedment and the predicted embedment. Then we have proposed the correction parameter for the original DNV based model that is known as model 2. So in the study data overview, we have considered the 118 kilometers of pipeline. The water depth varies from the 300 meter water depth to 730 meter water depth. That is the highest point. 3 different pipeline sizes has been considered, though we have installed many different pipeline sizes. And the project located in the east shore of India, and the seabed condition is very soft. It's ultra soft clay. And the surface of the seabed is almost like a liquid condition. That is the most driven point here. And all the pipelines were installed in the relaying method. So regarding the pipeline, 3 different pipelines were considered. That is a 15 by 10 inch pipe-in pipe, 8 inch pipe, and 6 inch pipe. I don't go into the details of these pipelines. All these 3 pipelines are rigid pipelines and the relay method were used. And the soil conditions, as I have highlighted, the surface is almost like a liquid state. Even at 0.3 meter, the liquid limit is it's below liquid limit. The undrained shear strength is almost 1.7 kilonewton per meter square. It also matches with the submerged unit weight of the soil, which is also very low. Mean value stays at almost 4.3 kilonewton per meter cube. So CPT data also confirms the enrichment of the clay, which I have shown here. So coming to the embedment measurement. So we have used the work class ROV to measure the embedment of this pipeline. So typical pipeline has been shown here. This is the embedment. And this is the laser 5-point survey we have carried out. And 1 measuring point at the top of the pipeline and 2 at the either side at 1.5 meter distance and 2 at the 6 meter from the central line of the pipelines. And we have measured at each 1 meter interval. So this is the plot compares the actual embedment as well as what we predicted. So here we can see here, this is the originally measured embedment data along with the 15 meter moving average data. And this is plotted together with the DNV based prediction models. These dotted lines represent the DNV based models. This is the low estimate and this is the best estimate model. This is the high estimate models. So in the embedment, for the design convenience, we always propose 3 set of embedment data or the friction factor values. One is low estimate, best estimate, and high estimate. Depends on the design scenario, whether we go for expansion or walking or buckling. We choose these parameters. Most probably, most of the scenarios we stay for best estimate embedment values. So here we can see that in all the three embedment cases, the prediction is not so accurate. You can see that high estimate embedment predictions, that is the DNV model 2, that matches closely with the best estimate embedment models. So similar observation we have made in the 8-inch pipeline also. You can see here the high estimate prediction even stays lower than the actual embedment values. So these zigzag lines you can see here, this is the actual embedment data. So this is the high estimate embedment point. You can see that high estimate embedment predictions using the DNV equation, that is still lower than the actual embedment values. And in terms of embedment value, you can see the 0.9 times of D. That means 0.9 times of overall diameter. That means almost the pipeline gets sunk into the seabed when it was installed. Similarly, for the 6-inch pipelines, the observation is absolutely similar. The entire pipeline gone in, almost 95% of the overall diameter of the pipeline got inside the seabed. So this is again the overall distribution plot, and the normal distribution plot matches well with the actual field embedment data you can see here. And the mean value of the field embedment, that is a 1.5 times of the diameter in case of 15-inch pipe-in-pipe cases. That means the pipeline has gone 1.5 times of diameter, overall diameter of inside the seabed. And here in this case, mean embedment is 1 times of diameter. That means the entire pipeline has gone inside the seabed. Here in this case also 95% has gone in. So how it matches with the actual prediction? So again we have done the study using the statistical estimator using 1-to-1 plot. Here you can see that the mean embedment data stays at the middle. That means the mean embedment data is matches with the high estimate prediction that close to the 1-to-1 plot. This point shows the high estimate embedment data prediction matches with the mean actual field embedment data. And the low estimate embedment is far lower than the actual embedment. And in terms of the low estimate and best estimate prediction is not working well. High estimate almost matches with the best estimate prediction. Similarly, in terms of soil, we can see that all the pipes shows the heavyweight behavior. So here you can see the V over D into SU. V is the sulfate of the pipeline, overall diameter, and the undrained shear strength of the pipeline. So when this V over D into SU greater than 2, we call it as the heavy pipe behavior. So all these pipelines shows the heavy pipe behavior, and a 15-inch pipeline, that is the heaviest pipe of all these three cases, that shows almost 15. That confirms the heavy pipe behavior. In terms of soil strength, the back analysis shows the actual undrained shear strength stays between the low estimate embedment and the best estimate embedment, not at the high estimate embedment. That means undrained shear strength in the actual field is lower than what we considered. So what we can do? So the prediction is not working well. So how we can make the prediction better in the DNV formulation? So the DNV formulation, all the parameters stays same. Only we change the K-lay factors. So that is the dynamic lay factors. So we believe that the installation effect in the deep water as well as the remolding parameter of the soil, these are the two parameters influence the embedment design. So that parameter is known as K-lay. Originally, I have shown that the K-lay factor is between 1 and 1.3. Now we have back calculated, keeping all the parameters same, only change these K-lay factors. Now the K-lay factor falls between 2 and 3. And then the actual embedment and the predicted embedment works well. Now what we can do in this kind of soils, we just change the K-lay factor and we do the analysis. It better predict the embedment values. So the conclusion, the field observed embedment in the east coast of offshore India is very soft and it's not working well for the embedment prediction models of DNV model 2. So we can adjust the K-lay factors, and even if we adjust the K-lay factor, we should keep in mind all these pipes exhibit the heavy pipe behavior. This is due to the very soft soil, and the seabed surface is almost at the liquid state. So we can adjust the scale factors and improve the predictions. One more thing is we can further improve this model by considering the installation effects, that is bottom lay tension as well as the vessel motion parameter. This is the key parameters. So when we install the pipeline, what is the sea state as well as the vessel motion? If we know these parameters, even we can predict or quantify this the embedment predictions. Yeah, thank you.
Thank you, Mr. Subramaniam. That was quite technical, in-depth on piping. Didn't know that this kind of a solution did exist. Well, changing gears, next, we've all heard about green hydrogen. In fact, a lot of discussion in IEW has been around how green hydrogen can become the next fuel. While this magic fuel, of course, is going to replace a lot of applications of gas, LNG, and so on, with widespread application in refinery, fertilizer, cement, and so on. There is a little fly in this ointment. How many of you know that, in fact, to transmit green hydrogen, you still need fossil fuel to make that happen, right? So it defeats the purpose if you still need fossil fuel to make green hydrogen be used, especially for ammonia cracking. But I think there is hope, and that's why we have Andrew here. Andrew is an engineer, principal engineer from Johnson Matthey in the UK, and he seems to have developed an innovative solution which also addresses this and makes this whole end-to-end green hydrogen cracking through ammonia green. Would love to understand more, Andrew. Over to you.
Well, thank you for the kind introduction. Good afternoon. I'm Andrew Layton, a principal process engineer from Johnson Matthey. I'm going to present to you JM's adapt ammonia cracking technology on the basis around the challenges of delivering this commercial technology. Firstly, a little introduction to what Johnson Matthey is. So Johnson Matthey has a strong, sustainable business which has consistently adapted over 200 years. Through this time, JN has innovated and adapted products and technologies to meet our customer needs. One of JM's strengths is its strong hydrogen technologies through process engineering, such as membrane fuels. Okay? Thank you. I'll just change that to my face. So it's proton membrane technology and fuel cells for electrolyzers. And JM also has licensed technologies for low carbon process technologies. So this has given JM a leadership position in hydrogen developing solutions to meet our customer needs, using our world-class science and technology to solve some of the problems of reducing carbon intensity. So how does ammonia cracking fit into the hydrogen supply chain? So for a decarbonized world, large quantities of hydrogen will need to be transported from long distances to address the mismatch in supply and demand between where renewable energy is available and areas of high energy demand, where liquefying hydrogen is currently expensive and requires lots of energy, which means hydrogen carriers are needed. So ammonia is widely recognized as one of the best options in terms of technology readiness, where approximately 20 million tons of ammonia is transported by ship each year so far. And therefore, ammonia benefits as a hydrogen carrier from established infrastructure, technologies, and standards. The benefit of ammonia as a carrier is that it contains no carbon atoms and therefore does not directly contribute any carbon dioxide emissions when it is combusted or converted back to hydrogen. To release the ammonia from to release the hydrogen from ammonia, it has to be cracked over a catalyst in a high temperature process. that has similarities to steam methane reforming. This cracking process is not done commercially at large scale, so customers are currently looking to de-risk and improve this technology. So what does Johnson Matthey offer in delivering the ammonia cracking technology? To meet the emergent need of ammonia cracking to serve future hydrogen trade with ammonia as a dominant carrier, JM has developed ammonia cracking based on customer needs. This is done by intimately developing the catalyst around the JM's process technologies to provide overall high efficient process technologies. This is critical for our customers, such as power utilities, where performance margins are particularly slim. So within process technologies, we offer robust catalyst solutions designed to enable decomposition of the ammonia, giving long catalyst life while withstanding the rigors of high temperature operation, and combined with process engineering to produce a reliable and efficient plants. This is from JM, having over 70 years experience in catalyst and process technologies, innovating with deep expertise in high temperature systems, and a proven track record in scaling hydrogen technologies. So what makes up an ammonia cracking flow sheet? In simple terms, we take refrigerated liquid ammonia and as the feed and pressurize it, followed by vaporization and superheating using process heat integration. Ammonia vapor is then cracked in a top-fired furnace reactor with a catalyst in the tubes to produce the hydrogen and nitrogen, where residual ammonia is removed in a scrubbing system, and hydrogen product to the specification needed is achieved in a pressure swing absorption system, with finally hydrogen being compressed to the final delivery pressure. So the waste gases from the PSA and the ammonia scrubbing system are utilized as fuel in the furnace, where we close the energy balance with a variable fuel energy source. Oh, I didn't realize that had things. There we go. Oh, go back. There we go. So one key degree of freedom is the variable fuel we use to close the energy balance within the plant. So the JM technology uses a combined flow sheet where we can utilize different fuels and switch seamlessly between them depending on the customer's needs to make the hydrogen product. So this presentation shows the trade-off between the fuels that we have to encounter. So natural gas firing, it minimizes the ammonia consumption, where we sacrifice carbon intensity of the process, whilst accepting a smaller plot space or plot area for the process. We can also utilize crack gas as the fuel. This minimizes the carbon footprint of the process, but using cracked fuel increases the plot space for the required plant, as we have to increase the cracker capacities to produce the hydrogen and service the fuel demands for the process. So ammonia firing offers the optimized ammonia consumption and plot space while minimizing the carbon footprint for the desired hydrogen production. So ammonia cracking, as you can see, uses unconventional fuels to provide the energy to the process through combustion. This provided a unique challenge to JM to offer the ammonia cracking flow sheet in combusting carbon-free fuels and carbon-containing fuels in the same flow sheet. Based on the basic properties of the fuels, ammonia, methane, and hydrogen, we can go through the advantages and disadvantages of each of the fuels. So ammonia is a carbon-free fuel and whilst we also achieve good flame stability because it has a comparable flammability range to ammonia. The disadvantage of ammonia is the initial ignition due to its high minimum ignition energy. And also the products of combustion of ammonia produce greenhouse gases such as nitrous oxides and acid-forming gases such as nitrogen oxides, and plus the possibility of incomplete combustion due to the low flame speed of nitrogen when combusted. Whereas methane is the current fuel of choice, primarily because the properties of methane for combustion are all relatively moderate, and this makes it an easy fuel to handle in combustion. The disadvantage in a decarbonized flow sheet is the release of CO2. The advantages of hydrogen as the fuel, again, it is carbon-free and achieves good flame stability over a wide range combined due to its flammability limits and its very low minimum ignition energy and high burner velocity. These also create disadvantages for hydrogen in that you produce high thermal NOx emissions because of the high burner velocity and high flame temperatures. Hydrogen also suffers from safety issues and challenges due to its wide flammability range and low minimum ignition energy, with risks of flashback and explosions. So to overcome the challenges of combustion using the unconventional fuels, Johnson Matthey with John Zink have undertaken full-scale burner testing and CFD modeling of the fuel mixtures to be used during the operation of the ammonia cracking technology. This demonstrated to JM that we can achieve stable flame operation over the range of fuel combustions that we encountered. The testing has allowed JM to understand the level of combustion byproducts, including the nitrogen oxides and nitrous oxides, and has allowed JM to include sufficiently designed abatement catalyst solutions within the technology to reduce these combustion byproducts to meet the regulatory levels. From the combustion heat and radiation released during the burner testing, confirm the heat transfer into the tubes required for the catalyst cracking. So this overall allowed JM's ammonia cracking technology to provide a reliable and robust route to commercial scale ammonia cracking. So lastly, a case study on the differences between ammonia cracking for the power sector and a typical syngas production plant. So traditionally, syngas plants would operate at fixed capacities, whereas power plants will operate under cyclical conditions. We chose power plants because the predominant use of the hydrogen product is for hydrogen power plants. So Mcdermott developed a detailed design aided by CFD modeling to ensure responses within the ammonia cracking plant can meet the variable flow rates. Power plants, by comparison, require rapid startup to be ready to deliver power load increases, but also economical to run when not needed. So we have developed a flow sheet that can operate under different startup conditions and to maximize the economic running of the ammonia cracking plant, ready for when the power is required. To meet the needs of the power plant ramp-up rates, JM are developing our understanding of the impacts of thermal and mechanical inertia within the process to develop and offer technical and process control solutions. And as mentioned, JM has investigated the combustion of high nitrogen containing fuels with Johns Inc. To offer technical solutions to overcome the low flame temperature, low flame speed, and limited flammability range. So to summarize ammonia cracking, and this is a simple graphic of the flow sheet components. So JM, as a result of expertise in catalyst and process technologies for high temperature operations, JM can offer a reliable technology proven on our steam methane reforming technology to reduce the risk of commercialization. Robust equipment design to operate with rapid changes in capacity while maintaining product quality and operational safety. We also offer competitive performance guarantees through the combination of process technology and catalyst offers. These being our Catalco series catalysts and emission abatement systems. And finally, we offer a low ammonia consumption optimized through process heat integration. Thank you very much.
Well, thank you, Andrew. Quite refreshing to see a new technology in this space, and hopefully over the coming years this gets into mainstream. Next, we have an interesting topic. How many of you know that the power interferences, AC interferences from power, actually silently eat away our pipelines of oil and gas, and companies end up spending a lot of cost, money, and effort in making that not happen. Thankfully, we have Abhinay Swarup here, who's an operational manager at IOCL, and he's going to talk about a cost-effective way of ensuring AC interference in pipelines are in check. So, Abhinay, over to you.
Good afternoon, everyone. First of all, thank you for such an introduction. Before this session actually began, Manan told us about the need for supply, storage, and transportation, and its criticality in our day-to-day operation life. Now, one of the important aspects in this process of supply, storage, and transportation is also protection. So it is very important that pipeline is one of the critical infrastructure of the country, and the country is itself having more than 50,000 plus kilometers of pipeline. Now, it is very, very much important that we are protecting those pipelines as well, so that the transportation part can be taken care of. Now, what has happened is recently, in near about 8-9 years, a phenomenon of AC interference has come up, in which the transmission line corridors, which are in the common ROW of the pipelines, are causing trouble to the infrastructure itself. Now, I will be talking about my experiences in this particular area of AC interference and how to reduce the cost involved in protecting our pipelines. So just a brief introduction about myself. I'm an operations manager posted at Sambalpur in IndianOil Corporation Limited. I am an ACE CP level 3 certified person, and I have an experience of handling more than 100 kilometer plus of pipelines and doing its maintenance. So this is how we will be going about. We will have a brief introduction about AC interference and what are the challenges associated with the corrosion which is happening because of this interference, and how we are actually trying to have a preventive maintenance to mitigate the effects of this AC interference. And then we will talk about the innovative ways which we have come up to reduce the cost involved, and some of the field case studies associated with those innovative steps which we have taken. And finally, we will conclude. So, as we can see, in IndianOil itself, we are dealing with more than 20,000 plus kilometers of pipelines. And when we are looking towards that size of network, it is having almost near about 40%, which comes around 8,000 kilometer plus pipeline, is in common ROW of the transmission lines, which are more than 220 kV plus. And since this right of way is very limited, so what happens is often these transmission lines are in a space of less than 100 meters with the pipeline itself. So this become a major concern for the pipelines, as huge AC interference is happening because of these high voltage transmission lines, and it causes corrosion. This is some basic overview of the country, in which we can see that the pipeline network is on one side, and on the other side we can see the map of the power line. You will be amazed to know that the pipelines is more than 50,000 kilometer plus, and we are having more than 1.5 lakh kilometer of transmission line, which is 220 kV plus. So you can imagine that almost for each pipeline, we are having some or other transmission line which is in parallel with the pipeline itself, and which is a huge source of corrosion in the pipeline. So the basic physics involves is that it is having, because of this transmission line, it is having one inductive coupling, in which the underground pipeline is experiencing some magnetic fields of the transmission line, because of which some AC voltage and current is being developed in the pipeline itself. And the another part is the above ground pipelines, which are in vicinity of the transmission line, have some capacitance effect, due to which some capacitive coupling is happening. And the third one is in which some lightning strike is happening, or some voltage spikes is coming, in which very high voltage is being transmitted to the area nearby pipelines, which is causing pipeline rupture as well as damage to the coatings, pipeline itself. So it is very important that these factors should be taken care of, and some methodologies should be developed so that the pipeline can be protected from these effects. So as per NICE guidelines, it has been recommended that the pipeline should have a potential less than 15 volts, and the AC current density which is induced because of these transmission lines should be less than 30 ampere meter square, when the DC current density, which is being towards cathodic protection of the pipeline, is greater than 1 ampere meter square. And if at all the DC current density because of cathodic protection is less than 1 ampere meter square, then the AC current density limit goes towards 100 ampere meter square. So anything above 100 ampere meter square is definitely causing corrosion in the pipeline, and it needs to be monitored. Now you can see some of the photographs of the AC corrosion, which is happening in various pipelines of the country. These are normally, a typical pipeline is of a thickness 6.5 mm. And in AC corrosion, we are experiencing corrosion rate as high as 1 mm per year. So you can imagine if 6 mm pipeline thickness is there and the corrosion rate is of 1 mm per year, the leakage can happen in only 4 to 5 years itself. So it's very important that it is to be taken care. And these type of rounded defects with the maximum depth at the center is being is happening in the pipeline, along with black deposits. So how to mitigate this? Basically, conventionally, what we are doing is we are carrying out modeling of the pipeline and determining how many of zinc anode or zinc ribbon has to be laid along with the pipeline, and that comes around for an average 100 kilometers of pipeline, we are having 3 to 4 kilometers of zinc ribbon that has to be laid in parallel with the pipeline. So what is the advantages? Disadvantages is the very high amount of high capex is involved. You have to invest lots of money to bring the mitigation and achieve the NACE standards current density. And with the laid pipeline, you have to do again excavation for 3 to 4 kilometers to lay these zinc ribbons. And again, after 4 or 5 years, some problems happens in the anode which have been provided for the mitigation, and you have to again replace it. So this is a cycle, and it requires huge huge cost to the corporation. So this is a schematic in which you can see there is a coated pipeline, and zinc ribbon anode is laid just beside it, almost 0.5 to 1 meter distance, and it is being connected with a solid state decoupler to provide mitigation to the pipeline from the effects of the transmission line. Now, what we have come up with is that many of the pipelines which have been laid has been provided with casing pipes. Normally in road crossings or traction crossings, railway traction crossings, various river crossings as well. In these, some submerged crossings or cased crossings have been provided, and they are bare pipes, bare uncoated pipes. They can also act as a very good grounding and can equally help in mitigation of the AC interference. So we have done so what we are doing is, instead of providing zinc ribbons, we are connecting the pipe with the help of solid state decoupler with the casing pipe to provide adequate grounding to the pipeline. Now, what advantage is we are getting that the existing network with carrier casing pipings are being utilized, which brings lots of saving to the corporation, and it reduces the AC current density to a very optimal level, and as well as in fault cases, the stress is reduced. So the pilot case was done at one of the pipelines, in which the initial AC voltage was 15.48, and the maximum AC current density we observed was around 300 plus ampere meter square. And when we applied this methodology at that place, you can see the AC voltage has reduced from 15 to almost 1.66 volts, and the average current density has reduced from 77 to 5.23, well below the required or permissible limit. And then this methodology was implemented in various projects. In one of the projects, the estimated cost of the mitigation was around 1.2 crores. And by utilizing 2 or 3 casings, we have reduced the cost to almost less than half of the total requirement, which is around 15 lakhs. So we have a total savings of around 60%. In another case study, there was this 116 kilometer total length, and we were having a common corridor of around 74 kilometers, in which more than 400 kV and 765 kV transmission lines were present. In that particular case, we have grounded around 3 road crossings and 1 railway crossings. And we can see that the cost of total mitigation has reduced from 50 lakhs to 10 lakhs, which is approximate savings of 80%. So definitely this particular methodology is bringing so much of cost saving, as well as it is bringing the total results within the permissible limit by not giving any extra cost to the existing pipelines. So both all the parameters, technical performance and advantages are there, as well as there is no chance of failure to the carrier casing pipeline, as these are uncoated pipelines and no damages will be happening because of the effects of AC interference. So the key takeaways, I must say that by utilization of the casing pipelines in the existing networks, it brings lots of savings because of the cost involved in the mitigation for the AC interference, and all the technical parameters are well within the permissible limits as recommended by the NACE standard, NACE SP 21424. And as we have seen in the pilot case study, as well as the 2 projects which we have done, that almost there is savings from 40 to 80% of the total cost which were actually involved in the mitigation process. Now what we are trying is that we are trying to have a proper methodology and standards inside the corporation itself, that this methodology can be implemented to various other projects, so that the existing network with existing facilities can be well protected. Thank you.
My team, I think with that, we conclude the session. Thanks a lot. speakers for educating us on these topics, and hopefully we see a lot more traction and progress on these new technologies in the infrastructure space. I was your chair for the session. My name is Manan Shah. I'm a partner with Kearney and work on these kind of topics on decarbonization, sustainability, oil and gas, energy, and so on. Happy to stay connected. Thank you.